Okay, good afternoon, everyone. I hope I'm audible. So, welcome to the next problem solving session for the course Fundamentals of Food Process Engineering. So, in this particular session, we'll be solving problems related to the week 7 syllabus that includes freezing and freeze drying concepts. Okay, in this particular week, we'll have a lot of theory based questions, and some of them will be numericals, majorly involving the freezing time calculation, which we'll be discussing in this session. Okay, we'll start with the questions. So, if you guys have any doubts, if you want me to slow down or repeat something, please let me know. Either unmute yourself or post it in the in-call messages. And if you know the answer, also you can do the same. Question 1. Which of the following statements are incorrect? A. The freezing involves the removal of both sensible heat and latent heat. And B. Freezing of the pure water exhibits sharp transitions between the different freezing periods. C. During the pre-cooling period, the temperature of water decreases to the freezing point as latent heat is removed. And D. During nucleation, the freezing point increases to 0 degrees. So, which of these statements are incorrect? Any clue which of these are incorrect? So before that, does anybody know what a freezing curve involves? Okay, so I'll show you some representative examples of how a freezing curve looks like. So the A panel here represents that of a pure water, and the B panel represents the freezing curve of a food particle. Okay, so here in both these kinds of materials, there are certain common characteristics. First is that when you have a material at some temperature, let's say 10 degrees, you need to first bring it down to the freezing point, which is then the crystal formation starts, and then the entire product starts freezing. So one of the first thing that is, let's take the example of a pure water. So when you move from A to B, you see that the temperature is drastically dropping. So in this case, this involves the removal of sensible heat, where you see a temperature change. Okay, so this A to B involves, A to S involves the removal of sensible heat. So S is the point of supercooling. So in this stage, you will have your product at the slightly below the freezing point, but still majority of the product will be in liquid state. That is, the entire product will be super cool, and this is the stage where your ice starts nucleating. Small ice crystals start nucleating. So S is the point where your majority of the product is liquid, even below the freezing point. Then once the ice starts crystallizing, you have the latent heat of fusion being released. That is, when liquid converts to solid, you will have the latent heat that is given out, and because of this latent heat being released, you will have a very slight increase in the temperature from S to B. And after this latent heat has been released, you will then see a constant temperature region from B to C. This is the major region where the phase transition happens. That is, more and more ice crystals start forming. They nucleate, they form bigger particles, and then it leads to complete ice formation by the point C. So S is where the crystal starts forming. By C, you will have almost the entire entire water being crystallized. So B to C is where the phase transition happens, and at this stage, there is no temperature change. When you look at pure water, there is no temperature change. So by the time C is at point C, your entire water is completely frozen. From there, any further cooling will result in a further drop in the temperature. So this region is known as pre-cooling. This region is known as post-cooling. So there are mainly three phases involved. The pre-cooling, the phase transition where the latent heat is removed, and then the post-cooling. So in both the pre-cooling and the post-cooling stage, it involves the removal of sensible heat. And from B to C, it involves the removal of latent heat. So the statement A is true. Freezing involves both the removal of sensible heat as well as latent heat. So, and the second statement, here you can see that in graph A, this exhibits that of pure water, whereas this is that of a food material. So you can clearly see that freezing of pure water involves much sharper transitions, whereas when it comes to food, you will actually see a much more gradual decrease. It's not actually this sharp also, it is much more gradual decrease that you will see in the temperature with respect to time. So the B statement is also true. And in the C statement, during the pre-cooling period, the temperature of the water decreases to the freezing point as latent heat is removed. So the C statement is only partially correct. During the pre-cooling period, which is this, the temperature of the water does definitely decrease to the freezing point, but it is not because of latent heat of removal. It is because you're simply cooling down the temperature and there's a temperature difference, which is why there is some kind of there's some temperature drop. It is not because of latent heat removal. Latent heat removal starts only after the point S, all the way till C. I hope this is clear. The same case for this also, from S to E, you will see some sort of phase transition. S to C, you will see some sort of phase transition happening. So this is where latent heat is removed. And then, so C is only partially correct, it is not entirely correct. And D, during nucleation, the freezing point increases to 0. That is at this stage. At S is where you have supercooled fluid, and once there is a nucleation that is happening, you will have the latent heat being removed, and because of that latent heat being removed during the nucleation stage, your temperature will slightly increase to the freezing point. That is to point B. So statement 4 is also correct. Now to summarize, during pre-cooling, the temperature of the water decreases, indicating that the sensible heat is removed. There is no phase transition involved, so there is no latent heat also removed. That is from point A to S. So the incorrect statement is option C. Is this part clear? The different stages in the freezing process. So this is the pre-cooling stage, this is the post-cooling stage. So in food you see that there are multiple other curves that are involved. It is not as straightforward as the pure water. This is because food materials will have a lot of solutes as well along with the water content. So from A to B, as usual, A to S, you will see sensible heat being removed, where you will get the super cold food. This is where the ice crystal starts nucleating. Because of the nucleation, you will have a slight removal of latent heat, which increases the freezing point to increases the temperature back to the freezing point, which is point B. And after that, you see actually a drop in the temperature. Unlike the pure water where it is pretty much stable, you see a drop in the temperature. This is because of a concept known as freezing point depression, which highly depends on the solute concentration. So higher the solute concentration, more is the dip in the freezing point. So as you start crystallizing the water, your water gets crystallized and your solute gets much more concentrated as the freezing process proceeds. As the freezing process proceeds, since the solute gets concentrated, the freezing point also kind of drops. This is known as the freezing point depression, which you might have learnt back in your school days. And once it reaches point C, at point C, one of the solute will be highly concentrated, because you start crystallizing the water out, your solute gets more and more concentrated, and at point C, it will reach a stage where one of the solute will no longer be soluble. That is, the solute will start crystallizing out. Till point C, it was the water that was crystallizing out. After point C, the solute will also start crystallizing out. Now, since the solute starts crystallizing out, there will be a latent heat of crystallization involved in this process. So this was just latent heat for water. Now there will be latent heat of crystallization for the solute as well. Because of that, again you will see a slight increase in the temperature because the latent heat is being removed. Then again you have some other crystallization that is happening of the solute, and then finally after the entire product including the solute and everything has been crystallized and solidified, then further increase in the temperature will lead to the post cooling stage where again the sensible heat is being removed. I hope this is clear. Is there any doubt in the freezing of the food material when compared to that of the pure water? Okay, if not, we'll move on to the next question. Question 2. In a blast freezing, A liquid refrigerant is used, B plate heat exchanger is used, C cold air is used, and D concentric heat exchanger is used. Which of these is the right option? So what involves in a blast freezing is that in a blast freezer, you will have all your food particles being stored in trays inside a big chamber or a room. And in this room, you will have air being continuously circulated inside the room. And what the so it is the food comes in contact with the cold air, and this cold air is generated by heat exchange between a cool refrigerant with the air. So you will have cold air passing through the food materials that helps it to freeze. Then it will circulate to the heat exchanger or a condenser heat exchanger where the air will be further cooled with the help of a refrigerant. And then this cold air will again recirculate inside the room. So the blast freezing is a direct contact freezing technique where the air inside the room is cooled by a refrigerant, and this cold air is what freezes the food product, and it is not the refrigerant directly. So the refrigerant passes its cold temperature. The heat is exchanged from the air to the refrigerant, so the air becomes cool, and then this cold air freezes the food product further. The cold air can either be forced or naturally circulated. So you can either have a pump that circulates the cold air, or it can leave it naturally to circulate. And this blast freezing can be done either in batch or continuous modes. So the answer to this question is option C. Moving to question 3. During the primary drying phase in a freeze drying, what is necessary to calculate the amount of heat required? A. Latent heat of vaporization, B. Latent heat of sublimation, C. Enthalpy of water vapor, and D. Specific heat of the product. So before we proceed, what is the freeze drying process and how is it different from freezing? So in a freeze drying process, you not only just crystallize the water, you will remove the water as well. Whereas in case of a freezing process, you will only crystallize the water and reduce its mobility. Whereas in a freeze drying process, you will freeze the entire product and subject it to very low pressures that will result in the sublimation of these ice crystals into water vapor directly. So in that stage, you are removing the water as well. And what happens in a freeze drying process is that you have a primary drying phase where the sublimation of free ice in the product happens to a vapor state, and hence the pressure is lower and the heat of the sublimation should be provided to enable primary drying. So you take a product, you freeze it completely so that all the water molecules are now crystallized. Then you subject the food to a very low pressure, and according to the according to the state graph of water, which we'll be explaining later on, So when you provide the latent heat of sublimation, whatever ice crystals are there, that will be directly converted into vapor, and this phase is known as the primary drying phase. So all you need to provide is the latent heat of sublimation, and that is required to calculate the total amount of heat required. So when you provide the latent heat of sublimation in the form of a heat, that will help in the sublimation of ice to water vapor, and that will automatically remove the water content from the food product, which is why it is known as freeze drying process. And so this is the primary drying phase. The secondary drying phase involves the removal of water molecules that are very bound to the product. So in the primary drying phase, you are only taking the free water molecules available. So there is something known as free water molecules and there is bound water molecules. So in the previous week, we had discussed what is bound water and what is free water. So primary drying phase involves the removal of the free water, whereas the secondary drying phase involves the removal of the bound water. So in this case, the answer is option B. That is, we provide latent heat of sublimation to directly convert the frozen ice to water vapor. And this is the entire concept of freeze drying. Question 4. The length of the supercooling period depends on the dash and dash. So A, type of food and the rate at which the heat is removed. B, the food temperature and the rate at which heat is absorbed. C, the rate at which heat is absorbed and the pressure. And D, type of food and pressure. So we discussed what the supercooling period is. So what could be the answer for this question?
You can also do it. I expect answer.
So during the freezing process, the food is cooled to below its initial freezing point. That is what was A to S in the graph, if you remember. The freezing curve, A to S is what happens when during the freezing, the food is cooled to below its initial freezing point. Then at the point, the water remains liquid although the temperature is below the freezing point, and this phenomena is known as supercooling, which may be 10 degrees below the freezing point as well. And this S point or the supercooling point is where the nucleation of the ice crystals begin. And the length of the supercooling period will now depend upon the type of food and the rate at which the heat is moved. So whether it is a sharp increase, that is from S to B. So S is the phase of supercooling. So depending on the kind of food that we are dealing with and the rate of heat removal. If the rate of heat removal is fast, then this will also be a sharp increase, S to B. The rate of heat removal is very slow, then you'll have a pretty broad curve from S to B, and then it will the phase transition period will start. So depending on the rate of your heat removal and the kind of food that you're dealing with, accordingly the heat generated will also be different. Based on the amount of free water that you have, the kind of crystals that are forming, and so on. So your freezing point will differ, and then your so your freezing point will differ, and the amount of heat generated will also differ, and hence the kind of food and the rate at which the heat is removed affects the length of the supercooling period. If your rate at which heat is removed is less, then the supercooling period will be larger. If the rate is higher, then the length will also be less. So it's inversely proportional. The answer is option A here. Moving to question 5. The factors that influence the rate of heat transfer during freezing are A, thermal conductivity of the food, B, area of the food available for heat transfer, C, temperature difference between the food and the freezing medium, and D, all of the above. So the rate of heat transfer equations are something that we have been discussing in multiple weeks so far. So what could be the answer to this question? Okay, let's consider that we have the food material in the form of a slab, and let TA be the temperature of the surrounding air, Ts be the temperature of the surface of the food material, and we often assume Ts is approximately equal to Ta. That is, there is not much temperature gradient between Ta and Ts, is some kind of an assumption that we often make. So the surface of the temperature that has been frozen already, the surface of the temperature that has been frozen already, is almost equivalent to the air around the air temperature around the food material, and Tf is the freezing point of the food material. So only when the food reaches its freezing point will it start crystallizing out. So these darker orange regions are the crystallized regions, and the light orange regions are the ones that are still yet to be frozen. So in this case, when we look at the heat transfer rate, this is how the Planck's equation looks like. So the rate of heat transfer is equal to area into Tf minus Ta, where Tf is the freezing point of the food, Ta is the air temperature, that is the surrounding cold air temperature, and H is the convective heat transfer, that is first the heat has to be transferred from the surface to the outside environment. Heat is being removed from the surface to the outside environment. So that involves the convective heat transfer. So you have a convective heat transfer coefficient, and inside the food material you have conduction happening. So you have the conduction, the thermal conductivity K, and X, which is the length of the food that has already been frozen. So whatever heat is being removed has to pass through this X region, that is the already frozen region, and then reach the surface, and then from the surface through convection it will reach the surrounding air. That is how heat is being removed. So your heat transfer rate is proportional to the area of the food available. It is proportional to the temperature difference between the food and the freezing medium, and it is also proportional to the thermal conductivity of the food. If you simplify this, it will actually be proportional to the thermal conductivity of the food. So yes, all the above factors influence the heat transfer rate during freezing, and hence the answer is option D. Hope this is clear. If there's any doubt in any of the questions, please let me know. We'll repeat that part again. Okay, moving to question 6. This is a numerical part which involves calculation of the freezing time. And this calculation of the freezing time is something that has been repeatedly asked in previous assignments. So we'll discuss both the kinds of questions that has been repeatedly asked. So this is question 6. 5 centimeter potato cubes are quick frozen in a blast freezer operating at minus 40 degrees Celsius with a surface heat transfer coefficient of 30 watt per meter square Kelvin. So the freezing point of the potato is measured as minus 1 degree Celsius, and the density of the potato is 1180 kg per meter cube. Calculate the expected freezing time for each of the cube, and also calculate the freezing time for 2.5 centimeter of the cubes frozen under the same conditions. And we have some additional data where the thermal conductivity is given as 2.5 watt per meter Kelvin, and the latent heat of crystallization is given as 274 kilojoule per kg. So before we proceed with this, we'll first look at what we have in hand right now. So let's say TA is the temperature of the surrounding air or the ambient air, which is minus 40 degrees Celsius. So TA will always be the temperature at which the freezer is being operated, which is minus 40 degrees Celsius. Then you have the heat transfer coefficient as 30 watt per meter square Kelvin. The freezing point temperature, the TF, is given as minus 1 degree Celsius. Density of the potato is given as 1180 kg per meter cube. And as of now, we'll assume that the length is 5 centimeter. Later on, we'll calculate what happens if the length is reduced to 2.5 centimeter. So here, the thermal conductivity is 2.5 watt per meter Kelvin, and the latent heat of crystallization given as lambda is equal to 274 kilojoule per kg. Okay. So one of the easiest ways of calculating the latent the time for freezing is through the Planck's equation. So the derivation of the Planck's equation has been discussed in the video lectures. So So if you want to look at those, you can go through the videos as well. So we use Planck's equation when we do not have any information regarding the sensible heat being removed. So here there is no mention of what sensible heat is being removed and what is happening. We don't have we don't have the specific heat capacity given for the material. We do not know what is the sensible heat being removed. So when no information regarding the sensible cooling has been given, there is only the freezing point. There's only the freezing point directly given. That is it's mentioned here that the potato is at -1 degree Celsius. So when you have only the freezing point given, the easiest equation to use is the Planck's equation for the calculation of freezing time. When you have a lot of the data given that we'll be discussing in the coming questions, at that time you can use a different equation which is much more accurate than the Planck's equation. So as of now, given the lack of much other data regarding the sensible cooling, we'll use the equation known as Planck's equation, where Tf, which is the freezing time, is equal to rho L divided by Tf minus Ta into Pa by H plus Ra square by K. So here rho is the density of the food, L is the latent heat of crystallization, Tf is the freezing temperature of the freezing point of the food, Ta is the temperature at which the freezer is being operated, that is the ambient air temperature. P and R are constants that differ with the kind of geometry that we're dealing with. So a cube will have a different P and R values, a cylinder will have a different one, and spheres will have a different one. So we'll discuss what P and R are for this particular question. So P and R are constants. A is the dimension of the potato cube, and H is the convective heat transfer coefficient, and K is the thermal conductivity. So so for a cube, when we're dealing with any cube material, so P is equal to 1 by 2 and R is equal to 1 by 8. The derivation for this particular equation is already given in the video lectures, but only for a cube is given. So if you want for a cylinder and a sphere, it's pretty much straightforward and it's very similar to the derivation that is given in the video lecture. So for as of now, we'll start with the information that P is equal to 1 by 2 and R is equal to 1 by 8 for a cube. When we substitute the values, we have a density as 1180 kg per meter cube. The latent heat of crystallization is is given in kilojoule per kg. We'll convert it into joules by multiplying into 1000. 274 into 1000 divided by Tf, which is the -1 degree Celsius, which is the freezing point, minus Ta, which is the temperature at which the freezer is being operated, that is -40. Then I'm substituting P and R as 1 by 2 and 1 by 8, and A is the length of the cube, which is 0.05, divided by H, which is the heat transfer coefficient, convective heat transfer coefficient, which is 30 watt per meter square Kelvin. Then you have here K, which is the thermal conductivity. So I'm just basically substituting the values that are given in the question. There's no other calculation involved. From that, you can see that the freezing time we get it in seconds because all of these are in SI units. So the freezing time is 7944 seconds, which when converted into hours is 2.2 hours. So that is the first part of the question. In the second part of the question, it is asked that what will be the freezing time if the length of the cube is being reduced to 2.5 centimeter, given that all the other conditions are the same, which means that the density latent heat of crystallization, Tf and Ta, H and K will remain the same. It is only the A that is going to change. That is the dimension of the cube that is going to change. So if A is equal to 25 centimeters or 0.025 meter, so 2.5 centimeter or 0.025 meter, I'm just basically substituting that instead of 0.05 here. When I substitute A as 0.025, my freezing time is now 3486.8 seconds, which is equal to 0.9 hours. The answer to this question is option C. So you can see here very clearly that if you reduce the dimension of your food, then your freezing time also drastically reduces. So the smaller the food particle you expose, more quicker is the freezing process. I hope this is clear. So when sensible cooling data is not given, you can assume it to be a Planck's equation, and then you can proceed with the calculation. So we have a lot of questions regarding Planck's equation throughout the session also, and throughout the previous week's assignment as well. So the P and R values for a cylinder and a sphere is given in the lecture videos. So in case you have to solve any problems for a cylinder or a sphere, you can use the P and R from the video lectures. Okay, moving to question 7. Is there any doubt so far? Anything that needs to be repeated? Okay, statement 1. Thawing is a longer process than freezing when temperature differences and other conditions are similar. And statement 2. During thawing, the initial rapid rise in the temperature is due to the absence of a significant layer of water around the food. So which of these statements are true and which of them are false? We'll start with statement 1. Is thawing a longer process than freezing? So what happens in the freezing is that you have, let's say, the similar diagram that I showed you here. If you have a block here, you're removing heat from, let's say, two different directions, from this side and from this side. So you can see that this particular dark orangish region starts becoming ice, and your liquid product is in the middle. So whatever heat transfer that needs to happen or heat removal that needs to happen has to come from your inner unfrozen layer through the ice and then to air. This is how freezing happens. So heat is removed through the ice block. So you have an ice deposition here, and whatever heat is being removed has to pass through this ice. Whereas in case of a thawing process, what will happen is these particular regions will first start turning into water. The center will still remain ice, but the surface regions will start forming water droplets and water layer. So at that time, whatever heat that you supply has to pass through the water layer and into the food material. So that is what is thawing. That is the reverse of freezing is the thawing process. So what happens, what is the difference between the freezing and the thawing process when it comes to time is that the conductivity of ice is much larger than conductivity of water. So that is, it is easier for heat to pass through ice than it takes to pass through water. So when a so if the heat transfer becomes very difficult to pass through water, then the time it takes to thaw the entire food will also increase. That is, it becomes difficult for heat to pass and get to the frozen layer. So you have to subject it to more time to completely thaw the food. So thawing is a longer process. That is, in order to make it more clear, when the frozen food is thawed using air or water, the surface ice melts to form a layer of water. That is, the dark orange that you saw in the previous diagram is where your water will start forming. And water has a lower thermal conductivity and lower thermal diffusivity than ice. And the surface layer of the water therefore reduces the rate at which the heat is conducted to the frozen interior. That is, it becomes more difficult to transfer heat to the frozen material. So this insulating effect increases as the layer of thawed food grows thicker and thicker. So as more and more you thaw the food, you will have more and more water getting accumulated. Because more water is getting accumulated, over time it becomes much more difficult to thaw the food. Because now you have a thick layer of water that is unable to penetrate the heat, and so over time the thawing process will slow down much more. So you require much longer time to completely thaw the food. In contrast to freezing, where increasing the thickness of ice causes the heat transfer to accelerate because of higher thermal conductivity of ice. So in case of a freezing process, as more and more ice is formed, the thermal conductivity increases now. So it becomes, over time, it becomes much more easier to transfer the heat in case of freezing. Whereas in case of a thawing process, it's the exact opposite. Hence, thawing is therefore a substantially longer process than freezing even when the temperature differences and other conditions are similar. This is because you have a large insulating layer of water during the thawing process. Given this information, statement 2 is true because when you just take out your frozen fruit from the freezer onto the room temperature, initially there will be a rapid rise in temperature because initially there is no water outside. Only slowly the things will start thawing and you'll have water deposition. But when you take it immediately at time t equal to 0, you will see a rapid rise in the temperature because of the absence of a significant layer of water around the food. And over time, the water layer will start accumulating and hence the rise in temperature will also decrease. So statement 1 is true and statement 2 is also true. So the answer is option A. Okay, moving to question 8. Match the following. You have different kinds of freezers here and examples of freezers on the second column. So you have A, slow freezers, B, quick freezers, C, rapid freezers, and D, ultra rapid freezers. And column 2 you have cryogenic freezer, plate freezers, still air freezers, and fluidized bed freezers. So any clue what the answer is? So what is an example of a slow freezer here? Which of these could possibly be a slow freezer? So freezers can be grouped according to the rate of movement of the ice front. That is, when you start freezing, you will have more and more accumulation of the ice. So faster the ice accumulates, more faster is the freezer. If you have a slow freezing or crystallization of the ice, then it's called a slow freezer. So depending on the rate of ice formation, or as we say, the movement of the ice front, that is, the ice will start forming from the surface to the center. So that movement of that ice from the surface to the center is known as the movement of ice front. So freezers can be grouped according to the rate at which the ice formation happens. So slow freezers are examples of slow freezers are still air freezers or cold stores. That is, you just have a large room with air circulating naturally inside it, cold air circulating naturally inside it, and that cold air will freeze your product. So that will be one of the slowest freezers because air is naturally being circulated and that will take a lot of time. When it comes to quick freezers, you have a larger movement of the ice front, you have a larger velocity of the air as well, and that is an example of air blast freezers where you have a proper circulation of the air happening through pumps or something. You literally just blast the airs, or you will keep your food between two plates. So you have a food material, let's say a block, you will have a cold plate on the top or you will have a cold plate at the bottom. You will have direct contact with the food. So that will help in quicker freezing of the food material. So air blast and plate freezers are example of quick freezers. So for A, it is the third option. For B, it is the second option. In case of rapid freezers, you have fluidized bed freezers. That is, you have a food particle that will act like a fluid because of cold air being circulated. You will have rapid cold air that is being circulated and your food particles will be behaving like a fluid in the presence of that air. So that results in, so your air is very much in contact with the food particles from all the sides. It's not just two sides or so. The food particle will, since it will be like a ball suspended in water that is continuously bouncing. So you will have the food particle being in contact with the cold air from all the directions. So hence it acts as a rapid freezer. And on top of that, your air velocity will also be pretty high so that the food material acts like a fluid. Because of this, fluidized bed freezers can be considered as rapid freezers. And ultra rapid freezers are cryogenic freezers where you have liquid nitrogen that is at extremely negative temperatures. We're talking about below -100. So when you have extremely low temperatures, when you have liquid nitrogen, you just subject your food to a few minutes or a few seconds. Within that, because of that low of a temperature, your freezing process will happen that quickly. So ultra rapid freezers, you will have your food material that is dipped for a very short amount of time in liquid nitrogen, and that is how ultra rapid freezers happen. So the ultra rapid example of ultra rapid freezers is cryogenic freezers. So A is 3, B is 2, C is 4, and D is 1. The answer is option C. Hope this is clear, the difference between all the 4 kind of freezers. Okay, question 9. The defrosting in a freeze dryer can be done by A, passing hot air, B, using a heating element, C, both A and B, and D, none of the above. So which of these is the correct answer? Yeah, the answer is option C. So in a defrosting becomes very important because if you have too much of ice deposition that is happening on the condenser, then it will be very difficult for the condenser to work. So what happens is in a freeze dryer, your ice will be converted into vapor, and from the vapor will then reach the condenser in the instrument, and it will immediately condense to ice on the condenser. So this removal is the ice deposition happens on the condenser. Now if you have too much of ice deposition happening in the condenser, the efficiency of the freeze drying process will reduce. So you need to quickly remove that ice. You need to defrost it and remove the ice as and when possible, so that it becomes easier to continue the freeze drying process. So defrosting is a very important process that needs to happen in the freeze drying technique. So defrosting is very important because if the ice deposition is very high in the condenser, it will not work further unless we defrost it properly. And this can be done by passing hot air, by hot water or steam, or using a heating element. So in this case, the answer is option C. Okay, so question 10. We'll have a true or false statement again. Statement 1. In a freeze drying, sublimation of water from the ice front occurs, whereas in the conventional drying, evaporation of water from the surface of the food takes place. And statement 2. Conventional drying takes place at reduced pressure and freeze drying at atmospheric pressure. So statement 1, is it true or false? In freeze drying, sublimation of water happens from the ice front, whereas in conventional drying, evaporation of water takes place from the surface. Yeah, statement 1 is true. So in the freeze drying process, you're trying to convert the ice directly to vapor. So whatever sublimation will happen at the surface of the ice, that is the ice front. Whereas in case of evaporation, the water that needs to be evaporated will start from the surface of the food. So statement 1 is true. And what about statement 2? Conventional drying takes place at reduced pressure and freeze drying takes place at atmospheric pressure. Yeah, statement 2 is false, because in order for sublimation to happen, you need to ensure that it is at a reduced pressure. If you do not reduce the pressure, then if you supply heat, all the ice will just turn into water. It will not turn into water vapor. So you need to reduce the pressure during the freeze drying process so that sublimation process can happen. Whereas conventional drying is just evaporation of water that can happen at atmospheric pressure. So statement 2 is false. The correct answer to this question is option B. So question 11. This is another kind of freezing time calculation, which involves a much more elaborate concept. So calculate the freezing time using FAMS method. So earlier we looked at Planck's method, which is the more simpler but inaccurate method. FAMS method is a little more difficult, but then it's a more accurate method. So calculate the freezing time using FAMS method for a spherical product. If the initial product temperature is 10 degrees Celsius, the air temperature is minus 40 degrees Celsius, and the product has a diameter of 7 centimeters. And the final center temperature is minus 18 degrees Celsius. The density of the unfrozen product is 1000 kg per meter cube. Density of the frozen product is 950 kg per meter cube. The moisture content of the product is 75%. The specific heat of unfrozen product is 3.6 kJ per kg, and that of the frozen product is 1.8 kJ per kg. The thermal conductivity of the frozen product is 1.2 watt per meter Kelvin, and Biot number is 1.46. So what you need to first notice is that here the initial product temperature is 10 degrees Celsius, but then finally you are reaching it at minus 18 degrees Celsius. And we know that 10 degrees Celsius cannot be the freezing point, because freezing point of water is much below, closer to 0 degrees Celsius. So first we need to cool the product from 10 to 0, or the freezing point, and then from that particular temperature to all the way to minus 18 degrees Celsius. So here you actually see a temperature of the product dropping, which is you have sensible cooling here. You're first bringing it to the freezing point, that involves sensible cooling. Then you're starting the crystallization, which involves the phase transition stage, and then you will further cool it to minus 18 degrees Celsius. So you have all the three: pre-cooling, phase transition, as well as post-cooling involved. The moment you have sensible cooling involved, you cannot use Planck's equation. You have to use FAMS equation or FAMS method. So what is not mentioned in the question, I'm just giving here because there is data missing in the question. We are assuming that the convective heat transfer coefficient is 50 watt per meter square Kelvin, and the latent heat of fusion or crystallization is 333.2 kilojoule per kg. With this data in hand, we need to calculate what is the freezing time. So the product has to come from 10 degrees Celsius all the way to minus 18 degrees Celsius. So we have the given here. Again, TA is the temperature at which the freezer is being operated, or the air temperature, which is minus 40 degrees Celsius. H is the convective heat transfer coefficient, given as 50 watt per meter square Kelvin. Ti, let it be the initial food temperature, which is 10 degrees Celsius. And Tc is the final temperature at the center of the food product, which is minus 18 degrees Celsius. And here you can actually see different densities for the frozen and the unfrozen product. So in a Planck's equation, it does not assume the difference at all. It just assumes that all the density, the specific heat is all the same before and after freezing. But in reality, that is not the case. So in FAMS equation, you have the ability to incorporate these differences as well during the freezing time calculation, which is why it is much more accurate. So the the density of the unfrozen product is 1000 kg per meter cube. Rho F is 950 kg per meter cube, and then the moisture content is 75%, which is 0.75. Again, you have the specific heat for unfrozen and frozen given as 3.6 kJ per kg and 1.8 kJ per kg. Then you have the thermal conductivity K, which is 1.2 watt per meter Kelvin, and latent heat of fusion, which is 333.2 kilojoule per kg. According to FAMS equation, the freezing time can be calculated as According to FAMS equation, the freezing time can be calculated as dC by EF into H, delta H1 by T1 plus delta H2 by T2 into 1 plus Biot number by 2. So this is a lot of parameters involved, where dC is the characteristic length. So if you're dealing with a spherical product, the characteristic length is the radius. So dC in the case of spherical product is the radius, that is the characteristic length. EF is the shape factor. So EF will depend upon whether you're dealing with a cube, a sphere, or a cylinder. So for a sphere, in this case, EF is equal to 3, which we'll be discussing in the coming slide. And then H is the convective heat transfer coefficient. Delta H1 is the enthalpy change during the pre-cooling stage. If you remember the graphs, it is from A to S. So during that stage, whatever enthalpy change is involved, that is delta H1. And the temperature change delta T1, and delta H2 is the enthalpy change during the phase transition and the post cooling. That is from B to C and C to D. If you remember, you have a phase transition which is pretty much almost a straight line, and then further cooling will result in again sensible cooling. From C to D, you will see a temperature drop. So delta H2 involves the enthalpy change during the phase stage and the post cooling stage. Delta T2 is the temperature difference at that stage. Bi is the Biot number. If you remember, that is the resistance due to conduction by resistance due to convection. That was discussed in one of the previous week lecture video, problem solving session as well as lecture videos. So Bi is a Biot number which is already given in the question. But the rest of this thing, we know EF is 3 for spherical particle, BC is the radius of the sphere which can be calculated. We have the diameter, we can calculate the radius. We know H, but we do not know what is delta H1, we do not know what is delta T1. We don't know all of these 4 parameters, which is what we need to calculate first. So let's say this is the delta H, let's say this is the mean freezing point. So your freezing point will be here somewhere, TF, and a mean freezing point will be somewhere here. Since latent heat of, the phase transition is not a straight line here. It's not parallel to the x-axis. You still see some minor drop in the temperature. So the mean freezing temperature will be somewhere here. Somewhere in between this entire phase transition. So delta H1, which is the enthalpy change occurring in the pre-cooling stage, that is this stage. In the pre-cooling stage, the enthalpy change delta H1 is equal to rho U, which is the density of the unfrozen product, because still here it is not yet frozen yet. You are just cooling the temperature. So density of the unfrozen product into Cp of the unfrozen product, Ti, which is the initial temperature, minus Tfm, which is the mean freezing point till here. This is the delta H1. The delta H2 involves the as I said, the enthalpy change during phase transition as well as post cooling. These two regions. So delta H2 involves rho F, which is now the density of the frozen product, because at this stage, once the phase transition starts, your product starts freezing. So rho F is the density of the frozen product, W is the moisture content, and lambda is the latent heat of crystallization or latent heat of fusion. So we are multiplying this into W because at this stage, it is the water that is getting crystallized out. It is not the entire food product. It is the water that is getting crystallized out. So you multiply this into the moisture content. Moisture content is basically the amount of water that is there. It is a measure of the amount of water that is there in the food. So you can multiply lambda with W, so that because it is only the water that is getting crystallized out. So this is for the phase transition region. And this is for the post cooling period, that is Cpf into Tfm, which is for the mean freezing point, minus Tc, which is the final temperature you want your product in. The center of the food product at the final stage. So this is delta H1 for the pre-cooling, delta H2 for phase transition as well as post-cooling. Where W is the moisture content, lambda is the latent heat, rho U and rho F are for density of unfrozen and frozen, Cpf and Cpu are for specific heat for frozen and unfrozen, and Tfm is the mean freezing temperature. And this is because this is not a straight line parallel to the x-axis. You still see some temperature drop. So you take the mean of this temperature as the freezing point. And generally this is an equation that has been found, that you can calculate the mean freezing temperature if you know what is the temperature at which you are operating the freezer and what is the final temperature that you want. So Tfm is equal to 1.8 plus 0.263 Tc. Tc is the final temperature of a food product in the center, plus 0.105 Ta, which is the temperature of the cold air that is being blasted in the freezer. So with this we can calculate Tfm. We already know the rest of the parameters. We know the density, we know the specific heat, we know Ti, we know Tc. We will calculate Tfm and calculate delta H1 and delta H2 finally. But we have just calculated delta H1 and delta H2. We still do not know what is delta T1 and what is delta T2 for the calculation of freezing time. So delta T1 is calculated as Ti plus Tfm divided by 2 minus Ta. All these are equations that you need to remember in order to apply. I don't think there's any derivation available in the video lectures. If you want a derivation, you'll have to go look in Google elsewhere. So delta T1 is equal to Ti plus Tfm by 2 minus Ta, and delta T2 is Tfm minus Ta. With this, we can calculate what is delta H1, delta H2, delta T1, delta T2, and substitute in the freezing time equation. So first we'll calculate what is the mean freezing temperature, TFM. So TFM is equal to 1.8 plus 0.263 into minus 18 degrees Celsius, which is your final temperature at the center of the food product, plus 0.105 Ta, which is the temperature of the air that is being blasted in the freezer. From this, if you substitute the values, you get the TFM as, or mean freezing temperature as, minus 7.134 degrees Celsius. So you can see the freezing point is not always 0 degrees Celsius. Depending on the food material, your TFM will change. This is equal to minus 7.134 degrees Celsius. And then we'll calculate delta T1. Delta T1 is Ti plus Tfm by 2 minus Ta. So Ti was the initial temperature of the food, which is 10 degrees Celsius. TFM you are substituting from what you have calculated so far, divided by 2 minus Ta, which is minus 40. I hope this is clear till now. Delta T1 comes out to be 41.43 degrees Celsius. Is there any doubt in calculating in what is delta H1, what is delta H2? This is a pretty longer, Cram's equation is a pretty longer question, but whereas Planck's equation is a much more simpler process. So we calculate delta T2, which is TFM minus Ta. TFM is minus 7.134, which we calculated. Ta is minus 40 degree, which comes out to be 32.87 degrees Celsius. So now we have delta T1, delta T2. We need to calculate what is delta H1 and what is delta H2. Delta H1 is rho u CPU into Ti minus TFM. So rho is 1000 kg per meter cube. You have CPF as 3.6 kilojoule per kg Kelvin. I am converting kilojoules into joules, so I multiplied into 1000. So 3600 into Ti, which is 10 degrees Celsius, TFM, which is minus 7.134. From there, you get delta H1 as 6.1 into 10 power 7 kilojoule, 6.1 into 10 power 7 joules. And again, delta H2 is rho F, which is 950 kg per meter cube. The moisture content, which is 75%, that's 0.75. And latent heat of fusion is given in kilojoule per kg, which is 333.2 kilojoule per kg. Again, I am converting all kilojoules into joules for SI units. So into 1000, I've multiplied it into 1000. That becomes 333200. That is 333.2 into 1000. Plus you have CPF, which is 1.8 kilojoule per kg. Again multiplied into 1000 to convert it into joules. And this is TFM minus TC. This is just substitution. As long as you remember the formula, it is just basic substitution that is involved, no other calculation. Delta H2 comes out to be 2.5 into 10 power 8 joules. So now I am just substituting back here. DC, as I told you, for a sphere, it is the radius is the characteristic length. EF for a sphere is 3. H and Biot number is already given. We have now calculated delta H1, delta H2, delta T1 and delta T2. So I am just substituting the values. The diameter was 7 centimeter. So the radius is 3.5 centimeters. So I am converting it into meters, 0.035. EF is 3 and H is 50 watt per meter square Kelvin. I am substituting delta H1 and delta T1, calculated from here, delta H2 and delta T2, 1 plus Biot number, which is given in the question, 1.46 divided by 2. From here we get the freezing time as 3744.67 seconds, which is equal to 1.04 hours. So this is how you calculate Fam's equation. Is there any doubt in the procedure? If in case you do not have a separate density for frozen and unfrozen, you can consider the parameters as same. If there is no rho u separately given, rho f separately given, you can just consider that the density was same throughout the frozen and unfrozen product. Okay, hope this is clear. Okay, question 12. The freezing time for a 10 centimeter thick block of fish is found to be 200 minutes when the freezing medium is minus 35 degrees Celsius. So you have the thickness given here, you have the freezing time already given, and you have the freezing medium temperature, which is TA, is minus 35 degrees Celsius. The initial freezing point of the fish is minus 1 degree Celsius. So it basically means that the fish is already at minus 1 degree Celsius. So when your fish is already at the freezing point, you can assume a Planck's equation instead of a Fam equation. Planck's equation is a much more easier process. So what will be the freezing time if the freezing medium temperature is changed to minus 25 degrees Celsius and all the other conditions remain the same? So we'll just discuss what is given here. TA1, that is the initial condition, the air was at minus 35 degrees Celsius. Thickness of the block A is 10 centimeter or 0.01 meter. The freezing point is given as minus 1 degree Celsius. Initially, if it is minus 35 degrees Celsius, the freezing time is found to be 200 minutes. Now, given that TA2 is minus 25 degrees Celsius, what is going to be the freezing time? So again, according to Planck's equation, we have this formula TF is equal to rho L by TF minus TA, PA by H plus RA square by K. Rho density, L latent heat of fusion, TF freezing point, TA temperature of air, P and R are constants depending on the geometry. A is the size of the material, H is convective heat transfer coefficient, and K is thermal conductivity. So for a cube, again, as we discussed before, P is equal to 1 by 2 and R is equal to 1 by 8. So let's say for condition 1, we are said that all the other condition remains the same, only the air temperature changes. So let's say we keep TA as TA1 in the equation. And similarly, for the second condition, let's keep the air temperature as TA2. So now you have two equations. Instead of solving it entirely, you can just divide the two equations. So TF2 by TF1 is equal to, if you divide, the rest of the parameters get cancelled, and you only have, if you simplify it, you will have TF minus TA1 by TF minus TA2. Because rho and rho will be cancelled if you divide. Against latent heat will be cancelled. This entire term PA by H plus RA square by K. Since none of the conditions change, this entire term will also get cancelled if you divide. Since only TA1, this particular parameter changes, so you will have TF2 by TF1 is equal to TF minus TA1 by capital TF minus TA2. So we have all the parameters required given in the question. So at the initial condition, freezing time is 200 minutes. The freezing temperature is given as minus 1 degree Celsius. Initially, the air condition is at minus 35 degrees Celsius. And when you change it to minus 25 degrees Celsius, that becomes your TA2. So you have minus 1 minus minus 35 divided by minus 1 minus minus 25. Which is TF2 is equal to now 34 by 24 into 200 minutes. So TF2 is now equal to 283.33 minutes. So here you can see, if you lower the temperature, it is less cold the air is, more time it takes. So if you had minus 35 degrees Celsius as your air, you had only 200 minutes. The moment you drop the air temperature to minus 25 degrees Celsius, your freezing time increases. So the air temperature also plays a significant role in the freezing time of a food product. The answer here is option C. So you have a lot of numerical questions regarding Planck's equation. Okay, question 13. At what point ice crystal formation takes place during the freezing process? A. Below the material's freezing point. B. Below the material's triple point. C. Below the material's dew point. And D. Just above the material's triple point. So what is the answer to this question? So yeah, below the material's triple point is where it freezes. So this is the phase diagram of water. So in this case, this is the triple point where all the three states coexist, the solid, liquid and gas. So the moment you reduce the temperature further, that is uh, below the triple point, you will see that all your liquid or your vapor, whatever the other states are, will now convert into the solid state. It is below the triple point, liquid can no longer exist and hence ice crystals form at the temperature below the triple point. So answer is option B. So as I mentioned, so this since only when you reduce the pressure, if you have a frozen material, only when you further reduce the pressure is sublimation possible directly from solid to gas, which is why in a freeze drying process, once you've completely frozen into a solid particle, you need to reduce the pressure significantly below the atmospheric pressure so that solid can directly convert into gas without going through the liquid phase, which is why in a freeze drying process you reduce the pressure. Okay, so question 14. We'll come to this question again later on because this is just similar to. Okay, we'll do this question. So, in an air blast freezer operating at minus 30 degrees Celsius, which is now your TA, blocks of fish of 0.0508 meter thickness are to be frozen. So, this is your dimension given. The initial temperature of the fish is minus 2.2 degrees Celsius and the moisture content is 82%. The heat transfer coefficient of the freezer H is 20 watt per meter square Kelvin. Calculate the freezing time in hours. And assume the density of the unfrozen fish as 1050 kg per meter cube. The thermal conductivity of the fish as 1.025 watt per meter Kelvin, which is K. Latent heat of fusion lambda is 335 kilojoule per kg. And the shape factors for an infinite slab, which is same as the cube. When you're looking at a slab, it is the same as the cube, which is equal to P equal to 1 by 2 and R equal to 1 by 8. So the moment you have P and R given, you know that you have to apply Planck's equation. And you do not have any information regarding the specific heat of the frozen and unfrozen product. So since no specific heat is given, you can assume that we are neglecting the sensible cooling process. So you can apply Planck's equation directly. So we have TA given, you have A, we have the freezing point TF given, we have moisture content, H which is the convective heat transfer coefficient, rho density given, K which is the thermal conductivity, lambda is given as the latent heat of fusion, P and R are given. So according to Planck's equation again, you have rho L divided by TF minus TA into PA by H plus RA square by K. So you have all the parameters, but what you need to understand one thing is that here you have an extra term as moisture content. So as I told you, it is the crystal that is only getting, it is the water that is getting crystallized and not the entire food, not the solute concentration, solute. So when you are multiplying your density into the latent heat of vaporization, you should consider only that of water. So since only the water molecules in the product is frozen and not the entire product, the latent heat of the fusion is now equal to lambda into W, where lambda is the heat of fusion given in the question and W is the moisture content that is there in the food. So L is equal to 335 into 0.82, which is 274.7 kilojoule per kg. This is very similar to the FAMS equation we used. There also there was moisture content given as 75%. So you multiplied the latent heat of fusion into the moisture content to finally calculate the actual latent heat of fusion. So when you have moisture content given, always multiply the latent heat of fusion into the moisture content given. So from this now we can just directly substitute the values since all of the parameters are given. So density is 1050 kg per meter cube. L, which we now calculated as 274.7 kilojoule per kg. I'm converting it into joules, so multiplying into 1000. TF was minus 2.2 degrees Celsius. TA, which is the air temperature, was minus 30 degrees Celsius. P and R are given as 1 by 2 and 1 by 8. The dimension of the slab was 0.0508 meters, which is what I'm substituting here. H was 20 watt per meter square Kelvin and K is 1.025 watt per meter Kelvin. So just the basic substitution, we get TF as 4.57 hours. So when you have moisture content given, please be careful to multiply that with the latent heat of fusion and then substitute it inside the formula. Whether it is a FAMS equation or Planck's equation, always multiply the latent heat of fusion with the moisture content. Okay, question 15. Dash are formed when crystallization takes place a long time. A. No crystals, B. Small crystals, C. Large crystals, and D. None of the above. So which of these? No, the answer is not B here. So when crystallization takes place for a longer time, we are looking at a slow freezing process. So you have two kinds of freezing process. You have a slow freezing process where you take a long time to freeze the entire product, and then you have a rapid freezing process, something like dipping it into liquid nitrogen or so. So what happens is that when you have a slow freezing process, you provide enough time for the ice crystals to nucleate, come together and form larger crystals. Whereas in case of a fast freezing process, the ice nucleates and immediately you would have frozen the product completely. So the kind of ice crystals that you get are very small because the freezing time is very less. But if you have a longer freezing time, you are providing it enough time for these crystals to come closer together and form bigger crystals. So as a freezing process takes place, ice crystals are formed in the intercellular space, which increases the solute concentration. This results in the diffusion of water from inside the cell to the outside, resulting in more water availability for the crystals to form and coalesce. So as the freezing process happens, your available water, that is the free water, gets reduced, and whatever water was there inside the cells, the free water outside the cells get frozen first, and then whatever water is inside the cell comes out. And when you have a slow freezing process, the water that comes out also freezes, coalesces and forms bigger crystals. So slow freezing allows this motion and provides enough time for the crystals to grow and coalesce, resulting in a larger crystal formation. And these large crystal formation punctures the cell membranes, resulting in damage, leak and loss of food quality. Whereas when you have a faster freezing process, you do not provide enough time for the water to come out of the cells. You just immediately freeze it. So there is not much damage to the food product, which is why people often prefer fast freezing processes. So the answer to this question is option C. When you have a longer time of freezing, you have larger crystals. Okay, question 16. Statement 1. Freezer burn results in irreversible changes in the color, texture, flavor and nutritive values of the food. And statement 2. Freezer burn takes place in unpackaged food in air blast freezers. Which of these statements are true or false? So statement 1, is it true? Yeah, freezer burn occurs when there is moisture loss from the food product, resulting in dehydration, shriveling of the product. Now, the moment you have loss of moisture, you are exposing and you have oxygen exposure as well. This results in oxidation of the food and changes in the pigmentation, hardening, and loss of nutrition. And this is especially seen uh, in meat products, where you can see a dry, grainy, and tough brownish area on the food. So statement 1 is true. This change is an irreversible change because of oxidation of the food happening, and oxidation can happen only if you do not completely pack the food properly. If you have unpacked food and when you keep it in an air blast freezer, it will have a direct contact with the air. And since it has now a direct contact with the air, the oxidation process also fastens and you have more freezer burn. Whereas in case of a properly packaged food, the probability of freezer burn is very less. So statement 2 is also true. Answer is option D here. So this is one of the cons of freezing processes. So you need to make sure that whatever freezing process happens, it happens in a very controlled environment with much lack of oxygen or with proper packaging of the food material. So this is again very similar to the question that we discussed, so I'm not using this again. Here instead of calculation of freezing time, we already have the freezing time, we just have to calculate the convective heat transfer coefficient. It's very similar to what we've been discussing so far, so I'm not discussing here in the interest of time. But if there is any doubt in this, you can contact me. Question 18. What are the limitations of Planck's equation for freezing time calculation? A. The density values of the frozen food are difficult to measure. B. Does not account for sensible heat changes. Constant thermal conductivity assumed. And D. All of the above. Yeah, the answer is D. So in case of Planck's equation, obviously as you keep freezing the material, the density of the frozen fluid becomes very difficult to measure. So when you cannot assume a single density and say that that is the same for frozen as well as unfrozen foods. So what Planck's equation does that it just assumes the density of the unfrozen foods and substitutes it inside the equation. But however, that will not be accurate. So that is one of the drawbacks of Planck's equation, where density of the frozen fluid is not at all considered because it is difficult to measure. And second thing is that in a freezing curve, the point A to B and after F is not at all considered in the Planck's equation. It considers only this point C to the D. So only the phase transition is considered, whereas when you talk about freezing time, it obviously involves the rest of the phases as well. So a Planck's equation does not give an accurate measure of the freezing time because it considers only the phase transition and not the sensible heat changes. And third is that the thermal conductivity is highly dependent upon the temperature. So as you drop the temperature, the thermal conductivity will definitely change. But Planck's equation assumes a constant thermal conductivity throughout the freezing process, which is not correct. So hence, all the options here are correct. All of these are limitations of the Planck's equation. Okay, question 19, last question for the session. So you have matched the following. You have column A, you have different kinds of freezing involved, and the second column you have the different kinds of freezer or the process involved. So which of these corresponds to which? So we discussed cryogenic freezing in one of the previous slides. So what does A correspond to? Yeah, A corresponds to 4, which is cryogenic freezing corresponds to liquid nitrogen and carbon dioxide. The individual quick freezing happens when you're looking at a fluidized bed because each and every particle is exposed to the coolant or the air through all the directions. So it is basically like you're taking individual particle and you're freezing it. It's equivalent to that. So individual quick freezing happens in a fluidized bed freezing where the particle is completely surrounded on all the sides by the cool air. And see, the plate type freezer is where conduction heat transfer happens. That is, from the plate, the cool plate, it is directly being transferred to the food material. So there is no convection involved. There is conduction, that is conduction across the plate to the food material. or rather the heat is being removed from the food to the plate. So you have conduction heat transfer involved. So it is C corresponds to 2. And in a scraped surface freezer, you have the raw material in the form of a slurry. So when you're dealing with slurry, they are extremely viscous in nature. And once you freeze it, it becomes all the more difficult to remove it. So you need kind of a scraper or so to scrape the surface and hence remove the frozen particles. So the answer is option B here. So with this, we wind up today's problem solving session. So if there's any other doubts so far, please let me know. We'll either be discussing today or we'll be discussing the next problem solving session. Yeah. So I'll be uploading this PPT immediately to the NPTEL site. So in case you guys are not able to access this, kindly let me know, and I'll be uploading the video also pretty soon. So is there any doubt in today's lecture? Okay. So with that, we'll wrap up today's class. Thank you.